we are soon going to begin. So that this will be about linguistic influences on mathematical thinking and cognition. So that the first talk is going to be by Ilaria. Am I saying this correctly? Saying
Yes.
the name correctly? Berteletti, which will be about sign language and its influence on arithmetic. I will then give a talk in collaboration with Daya Ganaim, who I see is now present, about the influences on arithmetic and number processing of the linguistic characteristics of the Arabic counting system. Then there will be a talk by Ilse Coolen and colleagues about influences on arithmetic and number processing of some contrasting European counting systems. And then HC Nürk will discuss the talks. So welcome everyone. And if Ilaria would like to begin.
Sure. Okay, can everybody see the slides? For accessibility, yes. I think I will ask all all guests, non-presenters and non on the panel to turn off their cameras so that those who need to see the interpreters have better, less confusing screens and can focus better. I will also try to be mindful and present each slide for a few seconds so that everybody can skim through the slide, and then we'll proceed with explaining. So thank you for joining us today. I'm going to present a research study using EEG to investigate the impact of language modality on the brain processes involved in arithmetic facts. This is now published, so if you're curious and want to know more, you can find the open source paper online. So here. So why is it important to understand how language modality impacts the brain networks? And when I talk about language modality, I'm referring to manual signed languages that are perceived visually. Well, all our studies so far have built the neurocognitive models using hearing and speaking participants. And we've kind of ignored the impact of a visual language and how this can change, modify, or not the networks involved in arithmetic processing. On the other hand, the translational implications are also very important because better understanding how a visual language supports arithmetic processing will also allow for better interventions, better practices for deaf signers, but most of all, hopefully better educational policies. First thing, let's talk about the impact of a visual language on the brain networks. So several studies have shown that early signers, deaf or hearing, activate the same language left lateralized network as hearing non-signers processing spoken languages. And this has been replicated in several studies, and we see activation in the inferior frontal gyrus and superior temporal gyruses as well. So it seems that those areas that process language really don't seem to care about whether a language is perceived visually or auditorily. However, sign languages and not deafness have shown to impact the brain. Some differences in white matter and cortical areas have been observed across brains, and also processing sign languages seems to recruit right lateralized areas in the temporal lobes that are not as much active for processing auditory languages. Furthermore, research from our programs has also shown that reading words, when reading words, deaf signers activate the motor areas, and these areas are activated more when the sign involves two versus one hand. There's also some cognitive changes that have been observed enhanced visual-spatial abilities, for example, as well as recruiting a visual-spatial phonological loop. But why is this important for arithmetic processing? Well, the arithmetic network is not fixed, and it's actually malleable. We've seen that it can change and be modulated by experience. Several studies on training and teaching practices have also shown differences, both real-time and long-term effects of the strategies used. And we've observed across-culture differences comparing Chinese and American participants, as well as within culture, comparing low SES with high SES, participants that have richer linguistic backgrounds, rich language environments recruit areas differently than those participants who have less rich language backgrounds, yet have similar performances. In our study, we're going to leverage two effects that are very robust in arithmetical cognition. One is the problem size effect on the left-hand side of our slide, and this has shown to rely on the IPS area, intraparietal sulci, bilaterally, with increasing problem size or magnitude, increased activations. EEG studies have found that problem size also modulates a later bilateral posterior component, and activations over this area seem to be modulated consistently with problem size, and also to be more evident on operations such as subtraction problems. On the right side, we have the operation type effect. Here we see that the neural networks involved are different depending on the operation type. Those problems that are recruited using verbal strategies and are memorized through verbal repetition recruit more language areas in the left hemisphere, whereas those problems that rely more on quantity processing activate the IPS more, and subtractions and multiplications have shown to have the most distinct neural networks. In the EEG studies, an early left lateralized component has shown an effect of operation type in prior studies. And this appears to be interpreted as a different allocation of attentional resources, supporting the distinct cognitive strategies. So our study is an EEG leveraging the ERP analysis and approach. We recruited deaf ASL signers who were exposed to ASL prior to age 2, and most importantly, attended deaf schools using ASL or deaf programs using ASL, or were attending school with interpreters, which means they learned their arithmetic problems in ASL. And then we also recruited English-speaking participants who had no ASL knowledge. We manipulated operation type, multiplications and subtractions, as these show the greatest distinction in the brain, and problem size. We had small and large problem sizes for both operations, but also added a third condition for subtraction problems, because if you look at the problems, large multiplications tend to be larger, much larger in magnitude than large subtractions. So to make sure that our effects were not related to operation type, but to problem size, we had to add this condition. On the right-hand side of the slide, you actually see the trial sequence. Participants started by seeing a fixation, then the operation sign came up, and that was to make sure that there were no across-trial errors by carrying over the same type of operation. The problem appeared, and participants had time to actually solve the problem in their head before seeing the solution. The solution could either be accurate or wrong, and participants were asked to hold in their mind whether it was right or wrong and answer on the next slide. and they would not know which side to provide their response because it was counterbalanced. The red cross and the green check were systematic counterbalanced. And this was made to avoid any motor preparation throughout the trial and throughout the period of processing we wanted to analyze. I will walk through each graph one after the other one and give time to observe each. So we're going to start with the leftmost graph. Here we observe that across groups, small multiplication problems were the ones with the highest accuracy. They were more accurate than large multiplication and more accurate than small subtraction problems. Now in the center, here we have a problem size by group interaction, which means that ASL signers showed the greatest problem size effect, with overall subtraction and multiplication together showing a lower performance for larger problems. On the right hand, it's only for subtraction problems. Here we see that both groups have a problem size effect. There is no group interaction. It was only separated for visualization purposes, where extra large problems were less accurate than large problems, who were also less accurate than small problems. Overall, we had no significant group differences. We observed our effects of interest of operation type and problem size, and we did observe a consistent problem size effect for subtraction problems. We did have a correction for multiple comparison using the Benjamini-Hochber false discovery rate formula across the entire studies, one for the behavioral results and one for the ERP results. ERP results are coming here. So we found a first early component that was left lateralized and showed modulation with operation type. And this component showed no quantity related effect and no interaction with group. Therefore, we suppose that this component is most likely an attentional component supporting cognitive processes that are differently involved in the two operations. The lateralization observed and the timing is consistent with prior studies and with our general predictions. We also found a later bilateral posterior component over the occipital and parietal channels. And here on the left-hand side, I have split the averages for ASL and English speakers, but there is, again, no group differences. This is only to see that the patterns are similar across the two groups. We see that subtraction problems show a problem size effect, with larger problems being less negative and multiplication problems showing no modulation and being more negative overall. The yellow highlights indicate the time window average in this analysis. And what is important to note is that if one might suppose that multiplications overall are larger in magnitude, they do have an opposite pattern of activation. If we looked on the right-hand side, our subtraction problems only, extra large problems had even less negative activations compared to large and small problems. So overall, we find distinct brain signatures for operation type and problem size, and the patterns are similar across groups. We were able to exclude that the results were related to problem magnitude of multiplications versus subtractions. Also, we were able to exclude that any of the effects were related to the number of digits in the problems, because our multiplication problems, regardless, were always more negative. And this suggests that there are different cognitive processes depending on the operation. So overall, we did not find any group effect and interaction with problem size or operation type in any of our components and for any of our analysis. Again, it suggests that there is a qualitative difference that emerges between the two. There is no qualitative difference emerging between the two language groups. And this is actually interesting, both theoretically and relevant for translational purposes. Theoretically is that even when considering a group of individuals who have a very drastic different life experience, that have learned their arithmetic problems through a visual spatial languages and have enhanced visual spatial skills, still multiplication rely on language networks and subtraction rely more on quantity process networks. This leads to ask us, why is our brain so stubborn and keeps on differentiating the operation kinds? From a translational perspective, this is even, I think, more important, because one may say, we did not find any difference. Okay, we were right. We can keep on going. Well, maybe we could, or maybe we could not, but from a translational perspective, this shows that sign languages are equal to spoken languages in how the brain develops. And there's a lot of countries out there and a lot of policies that are still based on myths about sign languages being lesser languages or not being full languages. And a lot of deaf children are still struggling to have access. And so bringing new evidence that even arithmetic can be processed similarly, regardless of language modality, is quite important to support adequate access to children around the world. With this, I'd like to thank my team, former students, current graduate students, and of course, the many arrays that come by. And thank you everyone for listening to my talk. We'll stop sharing this one.
Yes. Well, thank you very, very much. Does anybody have any questions? If not, then we will proceed now to the talk that I am giving. I do see.
And I have one question. Sorry, I have one question.
Please.
I just didn't want to be the first. But we have some minutes. Actually, it's a question I asked via email to Ilaria before, and I said I have a question. She said, but I have already an answer, so I would like to hear it. I mean, the obvious question is, one major conclusion of your talk is basically that you have null effects, that you have null differences. So, basically, and this triggers the absence of evidence versus evidence of absence questions, especially since EEG data can be very noisy and the sample was not so large. I know how hard it is to get sample. I'm very happy to see such a sample, but many EEG people would say under 50 between group comparison is critical. So basically, what is your answer about the power issues and the conclusions about the null effects? You're muted, Ilaria.
Yes, sorry. Yes, there are several considerations to be done. Yes, it is true. It is not a large sample size compared to other studies and the current trend in research. However, we do find effects. It's not like we don't find effects. We do find similar pattern of effects, which means that if we're missing something, it's in the order of the magnitudes. It's not a qualitative difference, I think. And regardless, even if we were to find qualitative difference, they're minor compared to the large effects we're seeing that are very important in developing proficiency in arithmetic. And indeed, this is not my last study. I have fMRI research that I want to bring for our in-person meeting soon if we get to go to Europe. And I'm continuing to investigate this topic because indeed there might be things that are not seen. However, there's also the other important side that is not only the theoretical perspective, but the translational perspective. Not seeing huge impacts does support the finding that is observed in reading literature that sign languages do support success in reading later on and also might be equally important and relevant for arithmetic success. This research is, I think, a first foundational evidence that sign languages support arithmetic. And we do see a lot of deaf children falling behind their peers very early. And this has brought to the wrong conclusion that sign languages are not helpful, but it's really the quality of the language access that is most important. And this is why also we really were very careful to find individuals that had no cochlear implant, that were exposed early to ASL, which is not that easy because most of deaf kids are born into hearing families and are not necessarily exposed early to sign languages. And so it's kind of, we're trying to work towards this question: what is the impact of language experience, and especially early versus late access? How does that impact? So, but yes, I agree, we should continue to study more and have better groups if possible. I will then stop my video if we don't have any more questions and mute myself, but share the slides for the next presenter.
Thank you. Okay, so I am now going to talk about the work done with Daya Ganaim, who is present and who may be able to answer questions that deal with Arabic itself, because he speaks Arabic and I speak very little. But it deals with writing units or decades first in two-digit number dictation tasks, bearing in mind that Arabic is an inverted language. Next slide, please. So in Arabic, the words numbers for 13 to 19 can be derived from the one-digit word numbers, whereas the word numbers for 11 and 12 are not consistent in this respect, fairly similar to English actually. And the order of unit and decade word numbers in two-digit numbers is reversed in Arabic, so that, for example, 18 is called 810, not too unlike the situation in English once again, and 27 is called the equivalent of 7 and 20, so that in many ways it is in these respects similar to German in the sense of having the inversion property. And after learning the teens, Arabic-speaking children also need to memorize the names of whole 10 numbers that are identical or similar to one-digit word numbers, adding suffixes to indicate that it's a decade at the end, as with English 60, 80, etc. So the Arabic equivalent. So next slide, please. So one important component of number processing is the ability to transcode between the oral and written counting systems. It's the ability to write a numeral to correspond to a spoken number word, or to read an Arabic numeral aloud. So that, for example, the numeral 4 can be spoken as vier in German, quatre in French, arba in Hebrew, arba'a in Arabic, and of course 4 in English. So that it's the numeral can be spoken in various ways, so that it's important to be able to write the numeral for the spoken word and to pronounce the numeral according to the spoken word. Next slide, please. So with two-digit numbers, they have a syntactic structure, was similar in many languages, of relating units to decades, and there is and the syntactic structure is transparent or less transparent according to the number category and the language, so that the numbers 10 to 20, mostly teen numbers. In English, the numerals 1, 5 are pronounced 15. The whole tens are, or decade number, the number 60 pronounced 60. In Chinese or Japanese, these would be more transparent, the equivalent of 10, 5 or 6 tens, but they are, in the languages we've been talking about, English, German, Arabic, Hebrew, they are fairly similar in level of transparency. And then other two-digit numbers include 23, which is pronounced 23 in English, but is 3 and 20 in German and in Arabic. So why are we studying Arabic? There is some evidence that transcoding and related skills, such as written number comparison, are easier in languages with transparent oral counting systems. These make the relationship between tens and units explicit, so the equivalent of 10, 1 instead of 11, 2 tens instead of 20, 2 tens, 1 instead of 21, etc. And such languages include Chinese and other East Asian languages and Welsh. Next slide, please. And studies of speakers of European languages have shown that children's and adults' transcoding and two-digit number comparison may be more difficult if their nut counting system has the inversion feature, i.e. the units precede the tens in the oral counting system, like 3 and 20 or 23 written. And examples of languages with the inversion feature for counting include German, Dutch, and Danish, and as we will discuss, Arabic. Next slide. So the Arabic written counting system is unusual in that, rather ironically, it doesn't use Arabic numerals, it uses Hindi numerals. But both systems have use base 10 and represent the place value system in identical ways. And in Arabic, as I've said, there is the inversion feature. Next slide, please. There's also difference from English and most European languages in terms of the reading and writing system. So Arabic, like Hebrew and Persian, is written from right to left, while numbers are written from left to right. So in Arabic, the order of units and decades in the oral counting system doesn't correspond with the order of units and decades in the written counting system, but does correspond with the direction of reading and writing words. In English and most European languages, the order of the units and decades in the oral counting system corresponds both with the order of units in the written counting system and the direction with the order of decades and units in the written counting system and the direction of reading and writing words. In Hebrew, the order of units and decades in the oral counting system does correspond with the order of units and decades in the written counting system, but doesn't correspond with the direction of word reading. And in German, Dutch, and Danish, the order of units and decades in the oral counting system doesn't correspond either with the order of units and decades in the written counting system, nor with the direction of word reading and writing. Next slide, please. So this study looks at how the transparency and inversion features of number words influence the pattern of two-digit number writing, especially the writing order of units and decades in transcoding to the dictation task, and we're looking at different ages. Next slide, please. So we had 77 pupils from primary school, 66 from junior high school, 72 from high school, and 72 from university. And all of the participants lived in Arab majority areas of Israel and spoke Arabic as their first language. Next slide, please. So they were given transcoding tasks, which consisted of the writing of 36 two-digit numbers pre-recorded by the experimenter. And they included numbers from 4 two-digit number categories, teen numbers, identical unit decade numbers like 22 and 23 and 33, whole tens numbers, decade numbers like 20 and 30 and 90, and other two-digit numbers, 23, 28, etc. And the order of presentation of numbers was random for each participant. Next slide. So the teens had the syntactic structure of units, and decades, whole tens, decade to suffix, identical ones, units to decades, and other two-digit numbers, units and decades. Slide. And the results show that in general, people did better for decade numbers and least well for the other two-digit number category, neither identical teens nor decades, but that the differences were most striking in younger individuals, and in particular, the primary school children did were wrong on the majority. Showed decade unit first writing pattern in the majority of cases for other two-digit numbers, while older individuals were much more likely to use a decade's first pattern for all numbers. It didn't when they used unit's first number pattern, it didn't necessarily mean inverted them. It could mean that they simply wrote down the units first and the decades afterwards, but it made inversion more likely. Next slide. So in general, Arabic speakers use the decades first writing strategy for transcoding two-digit numbers. There was an interaction between the educational level and the number categories, as I've just indicated, and the syntactic structure of the numerical system seems to affect the transcoding process, with the other two-digit numbers being most likely to be written with the units first, as they are spoken first. Next slide. Since whole tens are dictated with decades first, even primary school children adopt the decades first writing pattern, as is indeed used for number writing, but not text writing. For the other two-digit number category, the primary pupils adopt the units first writing pattern, which is used for text writing in Arabic, but the opposite direction to the standard number writing pattern, possibly placing less of a load on working memory. And even in later stages of education, pupils and students use the units first writing pattern more often for the other two-digit number category than for the other categories. Next slide. So in general, Arabic speakers adopt the decade first writing pattern for two-digit numbers, especially when it's consistent with their syntactic structure, as in whole tens numbers. This writing pattern increases as proficiency improves in mathematics and in second and third languages, i.e. Hebrew and English in this case. But this pattern is modulated by the complexity of the decade unit structure and presumably by the working memory capacity that's required to deal with it. And this complexity is most pronounced in numbers where it's important to keep the numerical syntactic structure in mind than when the syntactic structure is instantly transparent. There also appear to be effects of the consistency between the reading direction of text, right to left, the two-digit number reading direction, right to left, the taught number writing direction, left to right, which appear to influence the load placed on working memory, though further studies would be needed on how working memory is indeed affected by these. Next slide. Thanks. So, yes, thank you. And has anybody any questions? If not, we may proceed to the next talk, which will be by Ilse Coolen and follows on in a sense from this talk. And of course, people are welcome to email Daya or myself at a later stage if you have questions. Okay, so would Ilse now like to give her talk?
Yeah, so I'm gonna try and share my screen. Okay. Great. Okay, so I hope you can all see my screen. I promised you a talk about a translinguistic study between French, German, and English. Unfortunately, we only have the complete French data ready for now. So I'm just going to talk about the French number system and the influence that the French number system has on number processing. So why would I be interested in this? So I usually do research in children. And one of the tasks that I ask the children to do here in France is to write the number 190, as you can see here above in the slide. And quite often, so this I think was a 6-year-old child, quite often they write numbers such as these to respond to this. And that's because 190 is actually pronounced as 104, 20, 10. So it totally makes sense that they write this. So I wanted to look into this a little bit more. So to talk about the French number system. So basically they have a base 10 or decimal system from 1 to 60. So just like in English and like Anne already explained, so they say 10, 20, 30, 40, 50, 60. But as from 60 to 100, they use a base 20 system. So basically they don't have a decimal word for 70 or 90, but they count up from 60 to 80. So when they get to 70, instead of saying 70, they say 60, 10, and then 60, 11, and so on. And the same goes for 90. Here it's even more particular because they say 4 20s for 80. Hence why if you want to write 190, that you write 104, 20, 10, because 90 is actually 4 20s plus 10. So it's quite a complex system. There's, like Anne already nicely showed before, so that's really great. There's different language systems for number processing. For instance, the English, they have this base 10 system. The German also have this base 10 system, but they have this inversion. So instead of saying 99, they would say 9 and 90. although they would still write the digits as the decade first and then the unit second, as Anne already showed. And then the French have this partial base 20 system starting from 60. So why would this matter? So apparently I looked into this a little bit, and at one point in history, they wanted to maybe change this. So I know the French in Belgium and the French part in Switzerland, they, for instance, have a word for the decade 70 and 90. So it's only the French that actually do this. So at a certain point in history, they thought of maybe switching this system to be consistent and have decades from 1 to 100. But I think the French are quite proud and are proud of their, in my opinion, way too difficult language. And it didn't happen because why would you change something that doesn't cause a problem for the French people and maybe only for people from outside of France? Now, I would argue that this is not necessarily the case. First of all, remember this example where a child of, I think they were 6, has to write 119, writes 104, 2010. Second, there has been a study from Van Rinsveld and Shields who showed this, so who compared number transcoding between English and French children. I think they were about 10 years old. And the English children significantly outperformed the French in the number transcoding. But also in adults, there are language influences within number processing. So I like this study from Nürk et al. Because the title just works very well with this talk. So language effects in magnitude comparison, it's small but not irrelevant. So they looked into the compatibility effect, which I will be talking about later, and they found that the German had a slightly higher compatibility effect compared to the English. So there were still differences based on the language, which they hypothesized that was because the German have this inversion, which the English don't. So what is this compatibility effect? So the unidecade compatibility effect, in the first they thought that 2-digit numbers were processed holistically, but because of this unidecade compatibility effect, it shows that they are somewhat processed separately, the units and the decades. So for instance, you can have compatible, so unit-decade compatible trials and incompatible trials. Compatible trials are where the unit information and the decade information basically gives the same information. So when you have to show which number is larger, the 2 is smaller than the 7 and the 40 is smaller than the 50. So this is compatible because they give the same information. However, you can also have incompatible trials where the 40 here is smaller than the 60, but the 7 is larger than the 2. And indeed, they showed that incompatible number trials take longer to respond to compared to compatible number trials. Now, we wanted to check whether this was also true for base 20 compatibility, whether this base 20 compatibility could be found in the French language. This is what it would look like. So for instance, 67 and 98 would be a compatible trial because the base 20 decade 60 would be smaller than base 20 decade 80, which is the base 20 decade for 98. And the base 20 unit 7 would be smaller than the base 20 unit 18, which isn't technically a unit, but I don't have a better name for it right now. And you can also have incompatible trials. So the 60 is smaller than the 80, but the 13, which is base 20 unit, is larger than the 9. So we hypothesized that the incompatible number trials in the base 20 incompatibility would take longer to respond to compared to the compatible trials. Oops. So we created different conditions that would fall into one of these 4 cases. So just to give you some examples, so 67 and 98 is both base 10 and base 20 compatible. 73, 89 is, although it is base 20 incompatible, it is still base 10 compatible. 68 and 97 would then be base 10 incompatible, but base 20 compatible. And then you can also have base 10 and base 20 incompatible. So we created 600 stimuli. 50% was verbal, 50% was digit notation, so the verbal number word notation or digits. So basically we created 300 experimental trials from the beginning, which by experimental trials, I mean the numbers above 60. And we matched them on several levels, for instance, the unit distance, overall distance and problem size. However, there was a problem for the overall distance because we could only use the numbers from 60 and up, and there were basically not enough possibilities between number pairs to make all the conditions match perfectly on overall distance, as you can see here. So what we've done is that we created an extra 300 control trials, which are matched on overall distance and everything else as far as possible. And these are just numbers below 60, so they're control trials. So what we would expect is that we would have a base 20 compatibility effect in the over 60 numbers, but not in the control trials below 60. So we asked the participants which number was larger, and we showed them both in a verbal word notation and a digit notation. And then, so we have collected 372 participants online. 170 participants were excluded because of bilingual basis. 2 participants were excluded because they had been diagnosed with dyslexia or dyscalculia, and a further 21 participants were excluded after quality checks for the online data, if they had been interrupted or whether they were distracted during the task. So we are left with 179 French participants. You can clearly see that these are psychology students because 173 of them are female and the mean age was 20. So for the results, when looking only at digits, so we separated the analysis for the digits and for the verbal notation. So for the digits, we can see a clear base 20 compatibility, where the incompatible trials are responded to slower than the compatible trials. However, the same was true as well for the control data. So for the data below 60, the number pairs below 60. This could be 1 or 2 reasons, or both of them, which for now we don't have enough data yet, and I haven't gotten enough into details in the results to give you a clear conclusion. So it could be that this is just overall distance effect that is coming out here, and that thus shows a significant results in both conditions. It could also be that somehow the French participants, they have internalized this base 20 representations of numbers onto the numbers below 60 as well. We will be able to test this once we have the German and the English data, because we will be able to compare them, and we wouldn't expect the base 20 compatibility anywhere in the German or the English data. So if that's the case, then we could more easily conclude that it might be just generalized to number pairs below 60. And then we did the same for the verbal. So we just compared the base 20 incompatible trials with the compatible trials. And we found a base 20 compatibility effect in the verbal trials, in the experimental verbal trials above 60. And this time we couldn't replicate this in the control trials. So within the verbal trials, we can conclude that we find some base 20 compatibility effect. So very quickly to conclude, so we found a base 20 compatibility effect in the French number words above 60, not below. And there is still a possible base 20 compatibility effect in the French language in digits, which we do find, although we also find it in the numbers below 60. So if this is a base 20 compatibility effect, then it seems to generalize to numbers below 60 as well. And in order to conclude on this, we'll be able to control for German and English data and compare. So with the quote saying no need to change something that causes no problems for French people, I would argue that in children, but also in adults, it might still maybe not cause problems, but be a little tricky. Okay, so I'm gonna stop sharing my screen.
Right, okay. So I think maybe we should have the, okay, do I see a hand up?
So I think Ilaria has a question.
Ilaria, okay, so what is your question?
Yes, I find your topic or your conclusion a little provocative, since if I recall correctly, German language also is a little bit tricky for children, and inversion. And also I loved your comment how from a German perspective, you think French is hard. I tried studying German and there's no way I could learn German, although I'm successful in speaking French. So that was a funny comment. But yes, we've seen a lot of languages that cause issues, right? And we also know from other studies that actually the Chinese structure is the most transparent and the easiest one. Yet, would you argue that we should all change? And would you argue that these effects actually cause long-term difficulties?
So definitely not, and especially because I am definitely not an expert on language effects in numbers. So I think that's a really interesting topic maybe for the discussion later as well, because there's probably a lot of experts here. So I agree. So I speak Dutch, which also has the inversion property, which I didn't realize was actually a complexity until I was more fluent in English, and now I think it's ridiculously complicated to speak Dutch or to say two-digit numbers in Dutch. I'm not sure which one is the better system, and I don't think we should all just change to one or not immediately. The only main thing that I think is funny on the French is that they have a decimal system up to 60 and then a base 20 system beyond that, which I can't quite wrap my head around why it's only partly. But no, I can't say anything further on whether we should all change system and which system we could use, unfortunately.
But your comment on how you were not aware of the complexity of the Dutch system really parallels my experience. I was raised in Belgium and learned the Belgian French, and they have 70 and 90, but they do have the 80, the 80, the 420. And I have never thought about that word as being 420, but my perception of the word and the sound was just an 80 because I was not analyzing the parts of the words. However, it is true that 70, I could realize that 70 said in the French way, soixante-dix, the 10 part of the word was much more salient. So it is interesting to see. I don't know, I'm not familiar, maybe other people here, and we can maybe start the discussion. Do children in the early ages actually process these as holistic sounds and only later they compose them and become confused? And then once they go beyond the confusion, then they start showing again success, or is this confusion just right from the start? This is something I don't remember from reading the articles. Maybe someone can chime in here.
I can jump in. I mean, we find compatibility effects from first grade on, even before then they continue, the effect sizes continue to get stronger until fourth grade. So they have problems, and also in the errors. So basically you don't find errors in the compatible, or not many errors. I mean, I always find errors in children, but not many errors, and you find them more in the incompatible. So some of the children really have problems with the incompatible ones, basically to realize that the decade is decisive. And this is not only for magnitude comparison. We find it in number line estimation tasks. We find it in calculation, especially when it comes to carryovers. Silke Göbel has done that, who is in the audience. And we also have at least longitudinal data that children who have problems with inversion in transcoding in first grade and also with compatibility in first grade have also more problems with calculation in third grade. And that holds if you partial out IQ and other things. So so I do think in German it's some kind of a problem. It might be over. I mean, we still find, we still find effects in adults, like in magnitude comparison. It might not play a huge role in adults, but it plays a role in children, and it transfers from transcoding to other tasks up to calculation. And I'm married to a Polish wife, and when she has to, in German, when you have to give tip, you don't get the money. Basically the waiter is waiting for you. And if somebody tells her, even she speaks very well German now, somebody tells her that makes 57,37 € or so, she's like, it's like the horror, because she always has to quickly do the inversion. Also, she perfectly knows it and she can do it, but it's still a problem for her. So at least for people, who are not native, it's a problem, even if they speak the language well. And I do think if we would be looking hard enough, we would also find some residual traces in adults in German. Also, of course, people can compensate.
Okay, thank you.
Just another maybe comment from my side. The difficulty that we see, like on a conceptual level with the base 20 system starting at 670, is definitely reflected in the curriculum in France. That is, they learn the numbers pretty regularly, pretty quickly, until 69, and then there's a break. They don't go any further. And for young children in the first grade, that's easy. Like, okay, we didn't do that. We do this maybe next week. I don't know what's coming after 69. I don't care. So this is clearly reflected because they know it's difficult. They know there's an irregularity, and they take time to really in a separate session, and it takes an additional time to teach this to children.
Right, now, all very, very interesting. I think perhaps we should now proceed to the discussion, even though some of what we've just been talking about now is in a way a discussion. So Hans-Christoph Nürk will round off our session with some discussion of the important points.
I round off the beautiful symposium with a discussion talk. The discussion talk will not be a new talk about new data, but rather raise some conceptual questions about linguistic influence on numerical cognition. And it will be hopefully not short, not too long, so that we have some time for discussion. And I welcome you all. I mean, not also the speakers, but not only the speakers, to pick on one of the other discussion points I made. So basically, I think one thing to consider is when we talk about linguistic influence on numerical cognition, that this is a big, big melting pot, and however they can occur at very different levels. And Dowker and we had a special issue about linguistic influence numerical cognition in 2017, and now in our editorial, we basically made up 7 levels, which are from a language perspective very different levels actually, and we think they should be differentiated. One level is the lexical level, the lexical composition of words, in particular number words. This is what you, for instance, saw in Ilse Coolen's talk, Inversion, base 20, and so on. Then you have a syntactic level. Also, it's the lexical level is sometimes called syntactic, but I would prefer to do the syntactic level really to the grammatical structure of languages. An example is, for instance, that plural is right and dual is left, and singular is left, and some languages would have dual structure in grammar, which is then different again. Then we had one visual spatial orthographic level, where orthographic properties such as writing, reading direction of a language influence numerical processing. This is actually what Anne presented today about the Arab population. When you write from right to left, it changes all kinds of things, transcoding, snark effect. Then we have a conceptual level, conceptual properties of language above the syntactic and semantic level. An example is the markedness effect. So linguistic markedness influence how you process numbers. Odd numbers are on the left and even numbers are on the right. So I hope you have, this is translatable, because once when we did a study with signers in German Sign Language, they didn't have a word for parity and for odd and even, and we had to explain them, for instance, that 0 is an even number. So it seems to be different in American Sign Language. Then semantic meaning or existence of words, like from the neuropsychological side, you have that acalculics and aphasics have some deep meaning of words, of some words, number words. You can have the phonological level, phonological properties of languages can make a difference, and other things like working memory. So this was basically 2017. If you'd fill in the talks, you would probably say for Coolen base 20, this is lexical. For Ganyanim and Dowker, this is lexical, because you also have inversion in Arabic, visual spatial orthographic. And for Berteletti, I already have a question, because I didn't know exactly, and Ilaria might say something about it, where to put it, whether this is multiplication facts, verbal rote learning, it's linked to phonology, to verbal areas. But you know that many people also say maybe the phonology is not so decisive. It's really verbal memory, verbal long-term memory, verbal fact retrieval. And therefore, I proposed a minor revision of these seven factors. So actually, I think now that we should distinguish visual spatial directionality and orthographic, because, for instance, there are some data that orthographic properties of a language, for instance, might influence how numbers are processed. So if you have a more holistic language like Chinese, the compatibility effect might be smaller. Or with Julia Barnmüller, we have one paper with 3-digit numbers where we think that the onset rhyme structure in English compared to the grapheme phoneme structure in German might influence how you process multi-digit numbers. And then we think you should basically also add, or I think we should also add psychological concepts like verbal working memory and long-term memory, for instance, multiplication facts, verbal working memory, calculations with carry, and perhaps also language modality, spoken versus written number words seems to play a major role, as Ilse showed, for instance, in her talk. But even so, these are all different levels. Some might be more important, some might be less important. And based on that framework, I basically want to bring up some basic questions about linguistic influence on numerical cognition. The first question is generalization. This refers actually to the talk of Ilse Coolen. So what we already discussed, if these bases 20 effect just affect base 20 number words from 60 to 100 or 70 to 100, or whether they affect number representation beyond these concrete number words. And of course, this is not only relevant for Ilse's talk, this is a much more general question. For instance, if you actually look at the transparency of the number word structure in Asian numerals, this is mainly for 2-digit numbers. For instance, 300, 4,000 is very transparent in most Western languages as well. Nevertheless, maybe the more transparent number word structure, the more that children are able to learn the place value structure with more ease in the beginning, might generalize to a better place value understanding in general. Then, oh shit, something the difference between deaf signers. I'm sorry, not that. Probably it's between deaf signers and control, there are differences. Oh, I'm sorry. So some difference between deaf signers and control but have been observed, but not in their study. I mean, you showed some studies, one of us, where we found, for instance, subbase 5 effects, but not in your study, not with Arabic stimuli. And the question, of course, is code specificity. So, for instance, we didn't observe many differences, not so many differences to be precise, with Arabic stimuli, but we observed more with finger patterns, which are the same for hearing and not hearing persons in German, and with number words. So basically the code you might use might also trigger if you find language effects or not. Then stimulus specificity. I mean, this is one of the interviewing findings from Gallaudet and Dowker, which represent that basically for the decade numbers 20, 30, 40, there was less inverse writing direction for this basically whole tens, were written more from left to right in the children you investigated, while typical 2-digit numbers, no teens and the others, there was more reinversion, as we call it, more from right to left. Another example which we just study is the snark effect. So there is snark effect. For the snark effect, there is a working memory hypothesis that if you have to keep numbers or letters in your working memory, that the snark effect actually does not follow the magnitude of these numbers or letters or order of these letters, but it follows the order in working memory. And we are now finding this is not true in general. It depends really on the letter you're using. For instance, the letter A is always associated with the left side, no matter where it appears in working memory. Then individual specificity. So we have individual differences even for linguistic effects. For instance, the markedness effect I was talking about before, that odd numbers are associated with the left hand, and even numbers are associated with the right hand. This is actually mainly found in right-handers, but not so much for left-handers. And this reinversion strategy we found in a recent study with Julia Barnmüller, who is in the audience, that when people use the reinversion strategy in German, which Anne and Gallaudet have shown in Arab, they actually do it much less. But those people, those participants who do it, are specifically those with lower working memory skills. So basically, your individual working memory skills predict how you process numbers. And important interaction of linguistic with numerical process. I mean, I showed you all the different levels of the verbal linguistic levels, but of course we have also many different numerical processes, many different numerical levels. So basically in Berteletti, you found an interaction of the operation effect. If you wish to say this is a verbal effect, because multiplication is more verbal fact retrieval with problem size. And this is an example from taxonomy of Barnmüller et al., where we had the different linguistic levels here, but for place value processing, we have basically, don't go into detail, but we have basically 3 different place value processes: place identification, like in transcoding, place value activation, that you know what value is associated with what place, and computation, like in the carry effect, that you carry over. And if you look at the linguistic level and at a place value level, you see that not every level, at least, is influenced by every linguistic level, but you have to differentiate at both sides, at the linguistic sides and at place value sides, to show where there are influences and where there are maybe no influences. In the last basic topic are confounds of language and culture in cross-linguistic studies. There's a beautiful study by Anne Dowker, where she basically studied Hong Kong Chinese, Hong Kong English, and British English. And in her study, of course it's complex, and Anne can correct me, but the main finding is actually that the Hong Kong Chinese and the Hong Kong English were more similar in their performance than the British English and the Hong Kong English. So basically culture won over language transparency. And when you have such confounds, then I think it's important to have an effect-specific approach, that you look for effects rather than overall performance. And I brought you one example from a study of us by Pixner et al. So where we actually did a number line task with Austrian children who speak German with the inversion, and Italian children who speak Italian without any inversion. And then we looked, where did the Austrian children, at which specific numbers did they make more errors? And they made specifically more errors when inversion would lead you to the a wrong decision, which is major. So large interdigit distance would be numbers like 28 or 82. And if you have 28 and 82 and you mix them up as a young child, then of course you're at a very different place at a number line. And small differences would be 45 versus 54. So if you mix them up, there is not so much difference. And basically this is reflected in the estimation errors, that the Germans were not so much worse, or the German-speaking children were not so much worse for the small interdigit distance, but they were much worse for the large interdigit distance. And you can basically see the same with the direction. So for 82 and 28, an underestimation is provoked. So if you mix up 82 for 28, you go to the left. And if you mix up 27 for 72, or 77 and 20, as we say in German, as 72, you go to the right. And basically this kind of error was also larger in the Austrian German-speaking children, Italian-speaking children. So we did not only say they were somehow worse, but they were specifically worse in those conditions where inversion mix-up played a role. So that's my talk. Basically, these were the discussion topics: generalization, limitation, differentiation, stimulus and individual specificity, the interaction of linguistic and numerical processes that must be considered, and confounds between language and culture. Thank you for your attention.
Thank you very much. So has anybody got any comments? Okay, I see both Ilse and Ilaria would like to comment. So Ilse, would you like to comment first?
I don't necessarily have a comment. I just wanted to look at the people having a comment. But go ahead,
Ilaria?
Yes, thank you for your summary, very interesting. So I wanted to follow up on a couple of points you've raised. So I know your study about parity with German Sign Language users, and interesting, German Sign Language uses 2 hands for numbers up to 10, whereas ASL uses only 1 hand for numbers up to 10. So 6, 7, 8, 9, and 10, which makes it a very interesting property to compare the 2 sign languages. And what was more also interesting about your comment is that I was talking with a professor in the science department, actually a professor of statistics. She was commenting how parity seems to be hard for her students. They were not necessarily comfortable or confident about determining the parity of numbers. And so I do have a project about, I am thinking of investigating this more, because I'm also wondering the impact of language exposure. If many kids who are deaf start behind in being exposed to numbers and concepts related to numbers because they don't have language access, I'm wondering whether that is the main cause of this weak understanding of parity. But and I'm also open to ideas and collaborations or across sign language studies. That would be probably very, very interesting. The other comment is related to your comment about phonology in sign languages. So whether multiplications is phonology based or language based, verbal retrieval. And something that I think I was not aware, and maybe a lot of other here are not aware, is that when we think of phonology, we tend to have a confound and think of phonology tied to auditory information. However, sign languages have a phonology, and the phonology in sign languages is related to where the sign is produced, the hand shape, hand orientation, movement, and these characteristics actually activate the IFG areas. So it suggests that phonology is not related and tied to the auditory process, but more to the properties of the smallest part, informative aspect of a word or of a sign in this case. And so, yes, it makes us think that it's more language-based. And usually now I'm starting to transition more to talk about language-based processes rather than phonological processes. Or if we want to talk about phonological processes, these are non-modality specific. And I think this is still very interesting in our considerations about why multiplications rely on verbal or amodal phonological processes, and why it is so resistant in our brain that we continue, like whatever our experience, we will try to rely on those language-based processes rather than visuospatial processes. Or even if we were to train subtractions, we still go more to our IPS. And so that's definitely interesting. Here's my comment.
Yeah, thank you. I agree. I remember from Aachen also then that basically the language areas, also phonological areas, were more activated. I mean, you know that research much better than I do. And also that even more related that I don't know the English expression, but the mouse picture plays an important role. We had it in some of our stimuli that you should not cover the mouse with whatever stimuli or so, because otherwise the sign language is not really sign language anymore, but there is a very important feature which is not there. Yeah, so I definitely agree. I don't think sign language is visual spatial, and speech language is only phonological, but there are phonological areas also activated.
Yeah, we hopefully go. We will hopefully be at MCLS in Belgium, and I'll be able to show some data, some fMRI data on the role of phonological ASL processes in multiplication fact retrieval. So hopefully you'll come and attend and discuss further on that.
There is, I mean, I was interested in the discussion of culture and language, and that these are usually very difficult to tease apart. One thing that we have done with regards to the Welsh language is that we've been able to compare children in Welsh medium and English medium schools in Wales. And there are subtle cultural differences possible, but not nearly as much as between children in the UK and China, for example. And they are all being taught but to the same national curriculum, so that it's easier to look at the language specific effects when you do have people following the same curriculum, but that of course is often not possible.
Yeah, I mean, you're always in a quasi-experimental setting, and basically I think with English Welsh, of course, you don't have probably such big, there are some measures for cultural distance. You probably have a lesser cultural difference than between British and whatever Chinese children. But I think the one thing to overcome really, or at least to overcome not in a definite deterministic way, but in a probabilistic way, is when you really have specific effects. So when you have really specific effects like of inversion property and not just general processes. I mean, of course, you could in principle come up with alternative explanations, whatever somebody came up in the Italian curriculum, numbers like 28 and 82 are more trained in 45 or so than in the German curriculum, which probably which sounds relatively absurd to me, but people could come up with other hypotheses, but then these other hypotheses would have to be tested, and if somebody says this is more in the curriculum, then we would have to show data that this is the case. But when you have more specific effects, then you have a specific hypothesis, and then the counter argument that there are some cultural differences which are unspecific does not simply hold anymore. It only holds if you look at the global perspective, but not if you look at differential effects.
You're muted.
Yeah.
Yeah, thank you very, very much. That's very interesting. Yes, now, does anybody else have any further questions or comments? If not, or, I mean, does anyone wish to put a question in chat, for example? If there are no more questions, we might finish shortly, as we've had quite a long but very interesting session. And I'd like to thank everybody who spoke, and I'd like to thank Hans-Christoph Nürk for his discussion, and I'd like to thank everybody for attending.
Thank you for organizing, and
thank you.
Yeah, and to the interpreters, thank you for translating.
Thank you. Bye-bye.
Thank you.